Hello and welcome to Cracking the Cryptic. Now, today I'm going to introduce us to something that we've been meaning to look at for a while, which is, this is something from the listener crossword. Now, I use that word advisedly. The listener crossword is published every Saturday in the UK's Times newspaper and is traditionally thought of, certainly in this country, as the hardest cryptic crossword that's published on a regular basis. However, 4 times a year, once a quarter, the puzzle is not a crossword, but a sort of cross number or a numerical crossword. And I'm going to have a look at February's puzzle. This was around the 3rd week of February, I think, and it was listener crossword number 4595. The puzzle was called Equality by ELAP, and we'll go through the preamble in a moment. I am going to try and save a PDF that you could look at if you want to solve the puzzle on your own, and feel free. Now, the reason we're looking at this puzzle particularly is because it has what I considered to be an astonishing ending. So what I'm going to do in this video is kind of show you at least the start of a solution path that works. Just discuss how we go about doing the puzzle, and then go to the finish and explain why I think it was quite remarkable. So we get this puzzle looking like this, and then we get a long preamble and some clues. So I'm going to read the preamble. This puzzle is based on 9 sets of 6 numbers which have a remarkable relationship. Each set consists of 3 grid entries and the results of subtracting them in turn from the unclued entry at 16 across as follows. 16 across is a 3-digit entry in the grid. And then it lists these. There are all 3 clue numbers, and then the question marks are the results of subtracting the entries at those clue numbers from whatever the entry is at 16 across. And there's there's obviously 27 entries listed there. There's not many more than that in the puzzle. In fact, maybe there are only the 28 of those and 16 across. Anyway, this is all for the finish. Now, how do you solve it? Well, here we go. Each clue is an algebraic expression. So you can see that, for instance, 1 across is a plus f, whose value is the grid entry with the length given in brackets. That's the number of digits. The letters in clues represent different numbers greater than 1 that are powers of integers as follows, using the highest possible power. For example, 64 would be given as a 6th power, not as a square or cube. Then it lists these letters used in the clues, and you can see some of them, like there's 2 T's with capital 1 and a small t, and 2 I's. And I think we'll see why that is in a moment. And it gives that 11 of them are squares, 4 of them are cubes, 3 of them are 4th powers. There are 2 5th powers, 2 6th powers, and 1 8th power. Now, ordered by, so we can presumably just fill the grid with this information, that these clues using these values give answers that will fit the grid. And that's going to be the kind of technique to get there. Now, at the end it says, ordered by numeric value, so that's kind of in ascending order of the numbers. The clue letters will describe a property relating to the 6 numbers in each of the 9 sets that we were looking at earlier. This description refers to a value n, not related to any of the n's used in the clues. The property holds, so there is a property, and that holds for a series of consecutive integer values of n. Solvers must write below the grid the lowest and highest of these values, and we can see that below the grid we've got n equals something to something. To put that in. To reduce the amount of calculation required, ELAP guarantees that where the property holds for any 2 of the sets, it holds for all of them. Well, if we're using a program or spreadsheet, we won't need the amount of calculation required to be reduced, I believe. So what we have then is the grid looking like that, and these clues, and the information about squares and cubes and fourth powers. So what I'm going to do is just quickly mock up the grid in my crossword software, and we'll sort of look at how to solve it. Hang on a second. Okay, so here we are with the grid and the clues and this list of squares. Now the first thing I did was to create a spreadsheet which listed the possible squares, cubes, fourth powers, fifth powers, sixth powers, and eighth power. Now there's quite a lot of squares possible, but bear in mind that none of the grid entries are longer than 3 digits long. So you're only going to need higher powers than squares if they come within 3 digits mostly. So I made this list here of, so these are the powers along here, so a bunch of squares down there, and they kind of go on. Then only a certain number of cubes. I kind of went up to 4 digits or 5 digits just because occasionally you might have a minus sign in the clues that limit things. Now, there's 1/8 power, D. Now, where does that appear in the clues? Well, it appears in several of them, a couple of the down clues and a couple of the across clues, but 18 across is interesting. So 18 across is 3 digits long and is D plus S. So it's more than this 8th power. Now we know that the clues are different numbers greater than 1. So here are the 8th powers, and the only one greater than 1 that is less than 4 digits is 256. So we can actually conclude that D equals 256. That's very straightforward, and that in this clue it's 256 plus a cube, which is S, and that will give the value in at 18 across. Now, what are the cubes then? The cubes that are possible are these ones. So let's just copy that list onto this spreadsheet, and there's the list of possible cubes. Now, if we add 256 to those, these are the possible entries at 18 across. But bear in mind that the preamble was very specific that we're using the highest possible power. So if something's given as a cube, it's not a higher power. So 8, 27, 64 is a higher power of 2. So we can forget that one. That's not one of the possible values. 216, that is a higher power. This is where my maths lets me down a bit. No, that's a cube of 6. I don't think it's a higher power of anything else. 7, but 512 is, that's another power of 2. So we're down to these numbers, 264. These are the possible entries at 18 across. Now that means that the first digit is 2, 3, 4, or 5. And then we look at the grid again. Obviously the first digit crosses with 18 down. And this clue, the answer to 18 down, therefore begins with 2, 3, 4, or 5. Now the clue there is F times U plus little e plus P, and that's a 5th power times a square plus a cube plus a 4th power. Now the interesting thing there is that F is a 5th power, so its answer begins at, can't go beyond 599. What are the 5th powers? Well, there aren't many of them. It could be 32 or it could be 243. In fact, what are the two 5th powers used in the clues? They're F and I. Where's capital I? And look, both of them are used in the clue for 16 down, which is 3 digits. They add on a couple of other numbers, a couple of fourth powers actually, and it's still 3 digits. So neither F nor large I can be more than 1,000, and therefore they must be 32 and 243 in some order. So I don't know which order yet, but we get F and I are 32 and 243, or the other way around, 243 and 32. Now in this clue of F times U, which is another square plus a cube plus a fourth power, could F be as big as 243? It would have to be multiplied by a square, which can't be 1, so it would have to be at least 4. So we'd already be taking the number up to whatever that is, 800 and, well, nearly 900. No, nearly 1,000 actually. So it's far too high to be beginning with a 5. So F must be 32 and I must be 243. And again, you know, we get a bit of the equivalences done. We've worked on the 8th powers and the 5th powers now. So I haven't filled anything in the grid, and you know, I'm a long way from isolating which cube and which fourth power are involved in the clue to 18 down. But we do know that it can't be higher than, it's got to be below 600. So we've got 32 times a square. Yeah, I mean, there's a lot of possibilities to then add on even fourth powers and cubes. Now, where are the sixth powers in the clues? C and H. This C is not very helpful because you have to subtract a square from it, and that could be an enormous number. So C is not really telling us all that much as one of the sixth powers, but H is in the clue to 19 down. Is that in? Yeah, and that's interesting. That's connected in the grid to 18 across. Now, 18 across, the possibilities we've established are these 5. So it must begin 19 down with the ending digit of one of these, 1, 2, 3, 4, or 9. 19 down's clue is H, a sixth power, plus 2 P's, and P is a fourth power. Now what I would do there is kind of make a list of the 2 sixth powers that are possible, 64 and 729. So they're the 2 sixth powers that are possible for H. P then, which is a fourth power, could be any of these 60. It can't be 256 because that's a higher power of 2. Can't actually be, oh yes, it could be 16. Yes, sorry, for 256 is also an 8th power. I mean, we've used it already, so it's not that. So 16, 81, or 625 are the possibilities. And if we're adding 2 P's and 1 H, it kind of works out like this. Sorry if my Excel skills are way behind yours, that's really quite likely, but these are the possible entries for that 3-digit number that must begin with 1, 2, 3, 4, or 9. Now, which of those is a 3-digit entry that begins with 1, 2, 3, 4, or 9? Beautifully, only one of them. So 19 down must be 226, H must be 64, P must be 81, and we've really got to start going now. Let's put that in the equivalences. H must be 64, 81 is P. What was the answer? I said 226 is the grid entry. 226, and therefore the across entry, which ended in 2. Where was I keeping track of the possibilities there? Here, 472, and that means that S must be 216. So we've got another equivalence letter. And we can fill in 472 in the grid. Now we probably can't fill in 14 down, but we might know a little bit more about it. 18 down, which is F times U plus E plus P, where the E is a little p. So 32 times a square plus 81, we've solved that now. So we've got 32 times a square plus 81 plus little e, which is a cube. Okay, that's probably not actually going to tell us anything at the moment because we need a number that comes to 400 and something. We can restrict the cube u to, it's obviously got to be, sorry, the square u. It's obviously got to be something that won't multiply by 32 and get us past 500. So it's got to be within the range 4, 9, 25. That's it really, isn't it? Anything beyond that will take us too far. Well, actually, this might be worth working on because we could maybe get there. So we've got 4, 9, or 25. And if we multiply them by 32, then that's the FU part. Then we add P, which is 81. And then, so it's one of those numbers. 881 is clearly too high. We can rule that lot out. So 209 or 369 plus E, was it? Which is a cube. And that's going to give us a number beginning with 4. So what are the possible cubes? They are, well, let's just take those. Sorry, losing control here. And put them in here. So transpose them and just use values. In they go. And then we're going to add that. That's going to be, fix the H and the 6. Okay, so here are the possible values for that entry. There are 3 of them. 433, 494, and 425. And that means that for the cube, we could be looking at 64, 125, or 216. Now we've already used 64 and 216. There we go. So the cube that is represented by little e is 125. The answer to, and the u is 9. We know that as well. So we're getting lots more of these equivalences already. It hasn't taken very long. I can tell you that when I was solving this live, well, sorry, when I was solving it on my own originally, it took a lot longer than this to even get this far. But this is a good way to proceed. You have to, in these puzzles, oh sorry, what the entry was 494 as well. So fill that in, and you know we're making some nice bits of progress there. So yeah, the way to go about puzzles like this, especially with these numerical equivalences, is to try and find the clues that give you some restrictions. Like if you started with a plus f at the beginning, which is a square plus a 5th power to give you a 3-digit number, it could be anything. You can't limit that. But if you can find places where you can limit things, 3 down's quite interesting. For instance, it's a cube multiplied by itself. So you're squaring a cube, adding a couple of things to get a 3-digit number. One of the things is a 6th power, so there are some significant numbers going in there straight away. And if we look at the possibilities for squaring a cube, staying within 3 digits, 27 squared, yeah, that's okay, but obviously beyond that it's too much. But because 64 is not counting as a cube here, because it could be expressed as a 6th power. So clearly O is either 8 or 27. We haven't used either of those up yet, unfortunately, but let's just do a tiny bit of work on that and see if that gets us closer. So O is either 8 or 27. I'll just do an O there to remind me what I'm looking at. And we're multiplying it by itself to start the equation. 729, yeah, okay, 64 or 729 plus h plus w. Well, w is a square and they're fairly unbounded, but h is a 6th power. And the possibilities are 64 or 729, which are intriguingly exactly the same number that we were looking at there. Now, if you were to add 729 to 64 to 729, you would clearly go over the 3-digit maximum. But you could add 64 to either of those numbers, and now we're getting 128 and 793, and we have to add a square to that to get the entry at 3 down. Well, we can't necessarily make progress on that at the moment, but you can see that the way that the grid entries interlock to help you get information, well, actually, yes, that's quite an interesting little point. 14 down ends in an odd number. And that's made up of 2 little s's, which are squares, plus u. So you can tell from that alone that u must be an odd number. Because although u is a square and could be anything, s plus s must be even, because that's 2 times s. So u must be the odd number to allow that to end in 7. Now, as it happens, I think we already found out what u was, and it is an odd. Yeah, we could. That would have been another way to determine that u was an odd number. Now, what we have to do, and what I'm not going to do in this video, is go through all the clues and the grid and complete it. Now, you're obviously welcome to do that on your own. What I'm going to do is kind of jump to the finish. It's worth noting that 16 across doesn't have a clue, but all of its digits appear in other entries. So as long as you solve the other entries, 16 across eventually emerges. 16 across is important because that's the number that you then subtract all the other numbers from. So what I'm going to do is jump now to a finished grid. And we're going to look at the ending because I think the ending is what's most interesting here. So hang on just 1 second. So in fact, the finished grid turns out to be this, an interesting grid of numbers. There's nothing particularly remarkable, in my opinion, about those numbers as you look at them. We've found out now, rather unsurprisingly, 16 across has to be the largest entry, since we're going to deduct every other entry from it to leave a positive integer. And although one of the more interesting features of this is that that entry is 918, and a couple of the other entries are quite close to that, 914, 917. Now, let's remind ourselves about the preamble. What did it say we were going to do with these numbers? Well, each set of numbers consists of 3 grid entries. So for instance, the first set is 1 across, 5 across, 4 down, 816, 886, 529, and the results of subtracting them in turn from the unclued entry at 16 across as follows. So you subtract those from 918, you get 102, 32, And I can't do 529 from 918 in my head. 389. Okay, I can. That feels right. Okay, so that's a set of 6 numbers. There are these other sets of 6 numbers. And now, what's the rest of the preamble? Ordered by numeric value, the clue letters will describe a property relating to the 6 numbers in each of the 9 sets. Well, what are the clue numbers? And the answer is that I have drawn them out as, put them in order of what they were equivalent of. So we remember U was 9, and we found that F was 32, and we'd established P was 81, and some of the others. When you get them all in the clues and read down this line, it says sum of nth powers identical. So that describes a property relating to the 6 numbers in each of the 9 sets. This description refers to a value n. The property holds for a series of consecutive integer values of n. The property of sum of nth powers identical holds for each set. I mean, that seems ridiculous. So what I did up here was to create the lists of the entries. So we saw that that first set of entries was 816, 886 and 529. We subtract them from 916 and we get 102, 32 and 389. Now if we sum up, so what I've created here is 6 cells for each row that give the powers of those. If I enter a different power into this cell, we will see that this table here multiplies, or rather takes these numbers to that power. Obviously to the power of 1, 816 is 816, etc. But if you then add up those rows, you get 2754. And the same applies for each of those 9 sets of numbers. Well, okay, that's not astonishing that you can find 9 sets of numbers to the power of 1, i.e. the numbers themselves, that add up to the same number. But it is a bit remarkable if you can then square those numbers and they still add up to the same number. And look, I put the power of 2 in that cell, and indeed these numbers do add up now to a total of 1,893,442. So that's 816 squared plus 886 squared plus 529 squared plus 102 squared plus 32 squared plus 389 squared. And that equals the same as the sum of the squares of this row and of this row and of this row. I mean, that's just bizarre. How can that possibly happen? But what gets weirder is that you can change this power and it still happens. We'll go up to a cube. Yes, the numbers are still the same. I don't even know what this number is now. How big is that? I don't know how many digits we're talking there. Didn't get that right. Let's just try and do that again. So we're up to 10 digits. So it's 1,446,838,686. Let's take them up to a 4th power and see if it still works. Unbelievably, it does again. How can this be happening? I just don't understand enough about number theory to understand how that can be the case. Now we're up to 1 zillion, I think that is, 160 trillion, 901 million, no, 1 trillion, 160 billion, 901 million, 254,866. And that is the sum of all of these numbers taken to the 4th power in each of the sets. Well, I mean, that's crazy. And 5th power, does that work? Yes! It's now a 15-digit number that it adds to. It's just baffling. I mean, I cannot understand how this occurs. You try and take it to a 6th number and, oh God, the cell's not wide enough, but intriguingly, it doesn't work anymore. Now, finally, I mean, it's, you know, these numbers are quite close, 804 whatever this is, zillion, 805 and something zillion. It doesn't quite work for 6 or any higher powers, but it works for 5, it works for 4, it works for 3, it works for 2, and it works for 1. Now let's bear in mind that when we're entering, solvers must write below the grid the lowest and highest of those values. So this number n equals 1 to 5, but hang on, doesn't stop at 1. Because if you take the numbers to the power of 0, which makes them all 1, of course it must work. I mean, that's trivial, but you have to remember to include 0 as one of the powers in this puzzle. And the 6 ones add up to 6, and they're all the same. Now, you may be wondering, what about negative numbers? Well, I did try and take them to -1, and in fact, the numbers are slightly different. Now, these are rounded. I think if we add digits, yeah, they're not even vaguely similar. They're very different numbers. So it doesn't work for -1, but it does work for every number from 0 to 5. And I just think that's an incredible mathematical find. I'm not sure I can say that I begin to understand it, but it happened. And it's delightful when you work through a puzzle and you come to a conclusion like that. It's just an amazing thing. You know, maybe mathematicians can explain it to me. I believe the solution notes said it was an extension of the Prouhet-Tarry-Escott problem, in which only 2 sets are required. I don't know what that means. That's maths beyond my pay grade. But what a fascinating finish to a puzzle. Thank you very much to ELAP for that. Thanks to the Times for allowing us to publish their content occasionally. And I would never publish this before the closing date of the competition, which was March the 5th in this case. But I did want to introduce you to the amazing result and the amazing way that this compiler ELAP has turned this into a puzzle that encapsulates all these numbers. I mean, that's another thing to bear in mind, that he's fitted together these grid with these amazing set of 27 numbers and 918, which kind of governs them. And he's just managed to fit that all in together in a way that allows a solvable puzzle. It's an astonishing construction. I mean, I don't know. I've been doing these sorts of numerical crossword for years. The magazine that Simon and I founded, the Magpie, publishes one every month if you really want this sort of content, and who wouldn't? I mean, they're not normally finishing in quite this amazing way, but they are very, very much fun to solve, especially for people with a mathematical turn of mind. I've never seen one that finished like this before. This was just an astonishing thing. So just wanted to bring that to your attention. Hope you found that enjoyable in some way. If you had a go at the puzzle yourself, excellent. And I hope you got to the result and were as astonished as I was when I did. But thanks very much for watching, and hope to see you again soon on Cracking the Cryptic. Bye for now.